So I'm Tom Blue. I'm currently an intern at CrowdStrike, soon to probably be the intern at CrowdStrike. And I'm going to be talking about how the code compilation process works. So, why does understanding compilers matter? Compilers are tools which most of us will have used, and it's good to understand how the tools you use work. And it also helps us understand attack vectors that we otherwise would not have considered, which I'm going to get to. A competent computing professional knows about high-level programming and knows about hardware, and a compiler connects the two. So understanding compilation techniques is essential for understanding how programming languages and computers hang together. So let's start with looking at the compilation pipeline. You start with lexing, then parsing, semantic analysis, optimization, and code generation, and we're going to go into every one of those steps and explain what they are. So lexing. Lexing, it effectively gives meaning to characters in code. So let's take the string var a equals var b plus 100. The first thing the lexer will do is separate it out into characters. It'll strip white space and kind of group things together as tokens. And then those tokens are given meaning. So like var a, var b are identifiers, equal and plus are symbols, and 100 is an integer. So these tokens, known as lexemes, with meaning, get passed into the parser, the next part of the pipeline. So this takes these tokens, and the parser effectively enforces structure and catches syntax errors. It will generate what's known as a abstract syntax tree, which looks something like this. And this kind of gives a bit more meaning to those tokens generated by the lexer. So, like, looking at this tree, you can see that you're equating var a to the result of plus, and the result of plus is taking in var b and 100 as inputs. So var b plus 100 is assigned to var a. It gives more meaning to the lexemes that are passed in. So yeah, the parser allows you to think of the input not as a list of tokens, but kind of what you want those tokens to do. And we'll go more into parsing later as well. So this abstract syntax tree, which has been generated by the parser, will then be passed into what's called semantic analysis. Semantic analysis is very, very complicated and could be its own talk in and of itself. But I'm going to talk about two kind of parts of semantic analysis. Type checking and name binding. Type checking is just where you it's a process of enforcing types within values. So if you have var a equals words and you try adding an integer to it, that's going to result in a type error because it doesn't make sense to add an integer to a string. Similarly, if you're passing a value into a function, it's going to make sure that the value you're passing in is the right type, or else it will cause another type error. And type checking also deals with type inferences. So let's say we have var b equals func b 5. The type of var b is the return value of func b, but at this point in the pipeline, we don't know what func b returns, which is where name binding comes in. Name binding associates names to data, and so for example, in the example of func b, it'll associate the return value of func b to the name func b. So when func b appears, type checking can correctly infer what type will come out of func b. There's two types of name binding. There's static name binding, which takes place during compile time. So things like a direct function call. And there's dynamic name binding, which happens during runtime, such as dynamic dispatch. The only real difference is that dynamic name binding happens when you can't determine what the name will be bound to during compile time, like if you're calling a DLL, for example. So if we take this code as an example, we can see func b returns an integer, which means that if we apply type checking, the type inference of var b is an integer, and so when we compare var b to an integer, that's valid code because you're comparing an integer to an integer, which is allowed by, and you know that from type checking. So then, moving on to optimization. Optimization is also another massive topic and also could be its own talk in and of itself. But there's kind of two main optimizations where the majority of performance gains are achieved, which is inlining and partial evaluation. And inlining is basically putting functions within functions. So if you take this code, for example, you have func, which can either return a very, very long function, or b, which is literally just one line. What inlining does is it'll take b and it'll replace the call with the code from b, effectively meaning there's less function calls during the code. This has the side effect of making code longer, but it means that there's less context switching, and context switching is a very expensive operation for the CPU. The reason why we don't inline the very, very long function isn't just because it's going to massively increase the size of the code. So when your CPU is compiling code, it will cache the next few instructions. And if you jump past those instructions, it incurs what's called a cache miss, which will mean that the instructions have to be fetched from memory, which takes a long time and reduces performance. So by inlining a large function, if you then skip that function, you'll incur a cache miss, which will hurt performance, along with making the code much larger once compiled. But yeah, and the other part is partial evaluation, which is where you propagate known information during compile time. If the compiler can determine what a value might be during compile time, it can just replace that value with, it can replace the expression with the value it would result in during compile time, so that doesn't have to be evaluated during runtime. So for example, if you take this code again, assuming that var_c doesn't change before func is called, we know that var_c is going to be false, and so we know that the if statement is never going to enter the first branch. So we can just get rid of the first branch entirely. This is kind of an extreme example, but you can see how we've taken what was a little bit of code into and turned it into effectively one line, because we inlined function b and we used partial evaluation to determine that the very, very long function was never going to be called to begin with. Another part of partial evaluation is what's called constant folding. So if you have const a is equal to 533, for example, and we use const a in various places, you can just get rid of const a and replace the places where const a is called with is referred to with its value, which then also means we have this expression 533 plus 12, which is now something that we can determine during compile time. So we just replace that with its value, which again results in performance gains because it's less work to do during runtime. And then finally there's code generation. Code generation there isn't that much to say about it, but the three main steps are instruction selection, which is deciding which instructions to use. In complex instruction sets like Intel and like Intel's architecture, there are many, many instructions which can do the same things, and so instruction selection is where the compiler will determine which instructions are the most efficient to use in which places. And there's also instruction scheduling, which is what order to put those instructions in, which can have a surprising impact on performance. Previous to working at CrowdStrike, I was a researcher at the university, working on embedded system security, and I remember adding a single assembly instruction to some assembly I wrote, and that reduced the performance of the code by like 8 times, because it meant that due to the CPU and RAM running on different clock schedules, the CPU then had to wait for the RAM to sync up clocks, and it, like a single instruction, reduced performance massively. And then there's also register allocation, which is determining which registers which variables go into which registers. So that's the pipeline. But this is a very simplified pipeline. So if we were to look at what a real pipeline might look like, this is an example of what LLVM might look like. So you have lexing, parsing, semantic analysis still, but then you have what's called intermediate representation, which is kind of between your source code and the machine code that it ends in. And you apply optimizations on the intermediate representation over and over again, because once it's been optimized, you can then optimize the result of that even further. And as you do that more and more, the intermediate representation goes further from your source code and more to machine code. Another example, this is what C# would look like. C# does result in a .exe file, which makes it look like it might be compiled, but it isn't. It uses what's called a just-in-time compiler. So you get to intermediate representation, and that intermediate representation is passed into what's called a just-in-time compiler, which compiles your code as it's being run, hence the name. And optimizations are done during during the execution of the code. So you have this wall in between compile time and runtime. Everything behind the wall happens during compilation, and everything else happens during runtime. And then we have interpreters, which are again lexeme, parsing, semantic analysis, and intermediate representation. And then the intermediate representation is passed into what's called a virtual machine, and the virtual machine can go into either code generation or into an interpreter. The interpreter is a lot slower than code generation, but is able to extract more context out of what's being run, and can therefore feed that into optimization, so that when code generation is used, it can potentially achieve optimizations that you couldn't achieve during compile time. So everything after the virtual machine happens during runtime. I was considering making every diagram like this.
Coward.
But yeah, so let's go back and do parsing. Parsing, people seem to think it's like this super scary thing, but it's literally just a process of analyzing strings of symbols, and everybody parses. Like the sentences I'm saying right now, everybody's brains are parsing, because parsing applies to natural language as well. Parsing verifies syntax, but not semantics, which is why we need semantic analysis after parsing. So for example, the sentence colorless green egg is syntactically correct, but semantically colorless and green don't make any sense. So whilst this would pass, if we were pretending this was code, this would pass parsing, but semantic analysis would fail because the sentence doesn't make any sense. And in the context of programming languages and compilation, the parser turns formal grammars into abstract syntax trees, which was shown before. So what is a formal grammar? Grammars define the structure of languages. It defines kind of what the correct syntax is. And it goes through, you put the formal grammar through what's called a parser generator, which will result in a parser, which will then parse the formal grammar that you designed for your language. So yeah, you take the lexemes, you parse them, and then you parse them against the kind of formal grammar, and that's what creates the abstract syntax trees, which have more meaning. So taking this example again, a formal grammar for this might look something like this, where you have assignment being an integer plus an equals plus an expression being an integer plus and a plus and an integer. And you can also have the expression have multiple definitions. An expression could also be an integer, and an expression could be nothing. So if we look at the abstract syntax tree, you have addition, which matches the pattern for integer plus integer, assuming var b was an integer. And then we have assignment, which is an integer plus an equals plus an expression. And since the expression matches the first rule, we kind of simplify that into an expression, and we have an integer plus an equals plus an expression. So, yeah, I've just realized I kind of had cool animations for this, but I've already explained it, so. But yeah, so kind of a more general formal grammar we could create for this is this, where we have a value which could be any data type, a value which could be an expression, and a value could be nothing. And then we kind of create a language which will allow for the generation of a syntax tree, but also be more general and allow other types of syntax trees. And yeah, and yeah, so formal grammars are typically represented in what's called BNF. And this is what it would look like in BNF. So the first formal grammar I showed was kind of a simplified version to try and make it look less intimidating, because these symbols do look scary. The epsilon in value, by the way, just means nothing. So value equals epsilon pipe expression is just nothing or an expression. So if we were to look at a real-world example of a formal grammar, this is a formal grammar for JSON, and this is some JSON that will pass with it. So we notice that the apples are strings, and value includes a string literal, so we can replace those with values. And then we have pairs, which is a string literal colon value, and we have a string literal colon value twice. So then we can evaluate that to be a pair. Then we use the pairs and t-pairs rules to turn them into pairs. This is the reason why we have these kind of duplicate rules is because this grammar is designed for what's known as an LR1 parser, which has one look-ahead token. It's designed in such a way that you can evaluate the grammar whilst only looking at one token ahead, which is very good for code because it means you can more efficiently parse. The reason why natural languages isn't like that is because natural language is much more flexible than code and is therefore less efficient to parse. But yeah, so then we can turn the kind of curly braces with pairs into objects, and then we use the values the values rule to turn it into a values expression. And then that turns into pairs, and then that turns into an object. So you can kind of use the formal grammar for JSON to evaluate that JSON string into an object. And then that would obviously get passed into semantic analysis and would go through the rest of the chain. And the abstract syntax tree for this would look something like this. This is obviously massively shortened because it'd be absolutely huge. But, yeah. So the actual security bit, supply chain attacks. Well, so I've explained kind of how compilation works. And one thing to note is that compilers are compiled by compilers. And that means that if you have a malicious compiler which modifies the output of your code, you can have that propagate to other compilers quite easily. And this is from Ken Thompson wrote a paper in 1984 called Reflections on Trusting Trust, where he kind of explained this concept, and explained how you could kind of expand a C compiler by adding changes which would then propagate into whatever that compiler compiles. And if that compiler compiles another compiler, you could have the change propagate to that compiler and kind of have a supply chain attack which propagates throughout the entire supply chain. And this is obviously bad because you could have perfectly fine source code. A complete analysis of the source code won't find the vulnerability because the vulnerability is in the compiler. And it would make your otherwise benign code malicious during compilation. Which, this seems like quite a theoretical attack, and that's what I thought at first as well. But looking into it, there are a couple of real-world examples. So in 2015, 4,000 iOS apps were subverted by Xcode Ghost, which was a malicious version of Xcode that affected Angry Birds 2 and WeChat and various other apps. There was Octopus Scanner, which was quite cool, and it backdoored and spread through NetBeans projects by modifying the NetBeans compilation pipeline and propagating to loads of NetBeans programs over GitHub through the compilation pipeline. And then there was also Operation Shadowhammer, which in 2019 modified code compiled by Microsoft Visual Studio to make C and C++ programs compiled by Visual Studio malicious. So if you look at the Octopus Scanner in more detail, because I found the attack really cool and I just want to talk about it. The malware would first scan to see if NetBeans existed, and if it didn't, it would do nothing. But if it did, it would inject a dropper into every jar file. If you're not aware, a dropper is just, it it's some malicious code that will drop the actual payload somewhere in the file system and then run it. The idea being that you don't have to then spread the entire payload, you can just spread the dropper. And the actual payload typically was a remote access tool. So they were... So everyone infected by this would have a rat on their system. And it modified the compilation pipeline to ensure that the infection persisted and spread. So every time you compiled anything with that version of NetBeans on your PC, it would then inject the Octopus scanner into everything, which then meant when this was uploaded to GitHub, say someone clones it, modifies, uploads it again, not only have they kind of spread the malware even further, everything else that they now work on in NetBeans will also be infected with Octopus scanner. So, looking into it a bit further, I found that there was a remediation known as diverse double compilation. It was described in David A. Wheeler's 2009 PhD dissertation. And the idea basically is that if you have... so compilers come in what are known as families. When you have a compiler and you improve upon it, that's kind of the next generation of that family. And compilers from the same family will have certain similarities. And diverse double compilation is a way of using a trusted compiler within a family to verify the output of compilers that are a derivative of that compiler. The idea being that if you have one known good compiler within a family of compilers, you can then use that to verify every other compiler in that family of compilers. And it doesn't assume that DVC doesn't assume that two compilers will output the same binary. It just needs CA to be a derivative of CT. CA being the compiler which is being analyzed for a trust attack, and CT being the known good compiler. Some people might ask, if we have a known good compiler, why don't we just use that? But as compilers improve, the code that gets output is more and more efficient. And so by using a known good compiler that might be old, you're losing out on performance gains you might get by newer compilation techniques. I flew through that way faster than I expected, but that's the end. If you have any questions, then... Yeah,
with optimization, so you said that you can remove functions, and then that can, I guess, recursively remove a lot of functions, so it can also return static values. But then if at runtime your code is trying to access to memory these functions, at compilation time it wouldn't know that you're doing that. You'll be doing it at runtime, so that optimization will break the code.
So what would happen in that case? If you're referencing the part of memory where that function is, then that function won't be optimized, because it would break when you try to reference the memory where it exists. Yeah.
So before I get into my actual question, just to give you a bit more detail. Firstly, if you're writing code like that, don't. and secondly, if you need to write code like that, that's where keywords like volatile in C come into play. So you explicitly flag it in your code. The compiler knows, don't optimize this, I'm doing some dangerous stuff.
Yeah.
So my question for you, though, was a great talk, by the way, was we're seeing increasingly use of tools to do static code analysis before you then send it off to compilers or ship it out. How do static code analysis tools work? How does it compare to compilers? And what security implications might there be?
So, from my understanding, static code analysis tools analyze the source code to kind of find mostly common vulnerabilities like SQL injections, etc. This is something that would be subverted by a trust attack, because while the source code might be perfectly fine and secure and benign, the compilation is typically one of the last steps in the supply chain after QA, after static code analysis. So static code analysis does work quite well, and it's useful, and most organizations use it within their supply chain. But static code analysis usually works on source code, which could be completely fine in this context, but still output something malicious because there's an issue with the compiler. Yeah.
How do you compare the compile output from an early family, your trusted one, which is an early member of the family, to a later one, where all the optimizations are surely going. I mean, it could be more than just optimization changes. It's going to be outputting completely different binary code, I think. Well, not completely different, but heavily different.
So typically within families, kind of the way compilers implement things are the same. And I don't know exactly how it works. The PhD dissertation is very long and very complicated.
That's why it's a PhD dissertation.
Yeah, exactly. But it's basically, from my understanding, the idea that you're able to verify that the code functions the same as the output from the previous version without any actual kind of functional differences. And the reason why you need something from the same family is because the implementation details of how, like, what instructions will be chosen, how things will be implemented are typically the same throughout families. Yeah?
So, I'm a offensive security person. I'm not like a developer. But last year, what happened was the XSET library was backdoor by someone who tended to be an open source developer for years. So, in my mind, this sort of library dependency attack sounds along the same line of family of sort of the compiler propagation attack that you mentioned. So, would you see a big risk in big family sort of open source compiler like the GNU C compiler that a lot of people use, but the maintainers actually could become to social engineering? So, is it talked about enough?
That's a very interesting point. Open source compilers are kind of at risk to this kind of attack. And I've spoken to some companies who work, especially in cryptography, where a minor change could defeat cryptography and make something no longer cryptographically secure. And oftentimes organizations like that don't use open source compilers. They'll use compilers which are known good because of this kind of attack vector. I mean, obviously, if you were to, say, like with the octopus scanner, add a rat and have a bunch of network traffic, that's quite a noisy attack and would be detected quite quickly. But something smaller, like kind of changing how an encryption function works, a cryptographic function works, would be fairly quiet and might not be noticed for a long time. So it's kind of, open source compilers are at risk of this kind of thing. And a lot of companies that work on kind of cryptographic, on things which have to take this kind of attack into consideration often don't use open source compilers for that reason, or will use a known good version of an open source compiler.
And about standard compilers without any malicious intent, can we predict some level of certainty about some vulnerabilities some series of compilers produce?
Sorry, what do you mean?
Series of vulnerabilities.
Are they checking for vulnerabilities to compilers?
No. I mean, we have like C compiler, like 11.
Yeah.
And we know that any snippet it produces will be vulnerable to buffer overflows, to some injections, and with any modifications and further development, we can expect that these vulnerabilities will be in that applications anyway.
I think within most organizations, it's going back to static code analysis, where if there's a buffer overflow present on this.
About phasing, I would say more about phasing, because static code analysis is just statically deselect all these leak SEMs, right?
Yeah.
But about phasing, more about dynamic.
I'm not entirely sure, to be honest.
How would you say about supply chain and fuzzing all these possibilities?
Oh, do you mean fuzzing the binary at the end? I mean, I suppose that might work. It's not something I've looked at, so I couldn't really say for certain. But I definitely think, like, in areas where this kind of vulnerability is this kind of attack vector is kind of an issue. there should be some kind of analysis on the compiled binary, which fuzzing could be used for.
And about options, because when you compile, you have some options and you select optimizations, switch off some different configurations. How about this non-standard configuration?
Sorry, what do you mean?
Because when you compile, you just have configuration set up, target architecture, target, I don't know, cache structure, all this stuff. But when you fine-tune this configuration, you can produce some malicious.
Do you mean having compilers which might produce malicious code for certain configurations?
Yes.
I suppose then you'd have to kind of apply diverse double compilation to those specific compiler options. I mean, from what I understand, most of the time it's kind of during a trusting trust attack, the malicious code would be injected regardless of compilation options, just to kind of otherwise it would be very easy to accidentally avoid making your code malicious.
Yeah. Thank you. And about this again, supply chain that you mentioned. We already trust these compilers. We verified 1,000 times that structure, that architecture. But every day, every week, we have a lot of CVEs in legacy code, in some already trusted, already verified, because with different approach you can find something.
Yeah. A vulnerability in a compiler would be a different matter, because a compiler could be vulnerable kind of because of an oversight from the developers or something along those lines. This is looking more at an attack where a compiler is made malicious on purpose, where the vulnerabilities are injected by the compiler and kind of intentionally. Yeah, you could probably find many vulnerabilities in trusted compilers, but they generally wouldn't be injecting malicious code into your applications. Any more questions? All right, I suppose that's it then.